Question 3. Current electricity. In order to investigate the variation of current I with a variable resistor with potential difference V across it, a student sets up the following circuit. So we've got the circuit here. It's basically a series circuit. You've got your this is your variable resistor over here. You've got your ammeter, which is measuring the current through the circuit, both through the cell and through the resistor, and you've got your V, which is measuring your potential difference across your variable resistor. So we've got this graph. This is the V against the I, your potential difference against your current in the circuit. Now it says use the graph to deduce that for the battery the EMF is 4.5. Now let's firstly just look at our formula for EMF. Is this one over here, that the EMF is equal to IR plus R, where this R is the internal resistance in the cell itself. So it's the R in the cell, and this is the R of the circuit. Now if I multiply this bracket out, I'm going to get IR plus I small r. Now this IR over here is actually what your voltmeter is going to read. So I could rewrite this as E is equal to V plus IR. Now in looking at that, we see that our EMF is going to equal our V when I is 0. So when I have 0 I, I'm actually going to be able to measure my EMF. Now this is because when my current is 0, then this voltage over here will read the EMF, because if your I is equal to 0, there is no current flowing through that cell, and therefore there is no loss of energy within the cell of IR, the potential difference loss per coulomb of charge. So when your I is equal to 0, this is equal to 0, and therefore your V is equal to the EMF, or the maximum energy that can be provided by the cell. So all I've got to do basically is I've got to extend this line up like that, and you can read that off, and that's 4.5. So you need to state that the EMF, this is when your I is equal to 0. It's your basically your vertical intercept. Extend that line, V is equal to 4.5. The EMF is equal to 4.5 volts. Now looking at the internal resistance, now there's two ways that you can actually find this. Let me just clear the board. Going back to this formula over here, let me just redo this formula. So we had E is equal to V plus IR. Remember I did that. Now if we think of a straight line graph, Y is equal to MX plus C, we would see here that this is our X and this is our Y. So the R is your slope. So the slope of this line, or the gradient of this line, is equal to the small r. So if I extend it up as before, I extend that down like that, I will get, when looking at that, I will get, this is over there is about 4.5, and this over here is about 3.7. So I've got 4.5 divided by 3.7, and that works out to be about 1.2 ohms. Roughly about that. Now there's another way that you can also do it. Let's look at that. We know that when we have our V is equal to 0, so if I extend this down here like that, the V is equal to 0, because going back to this formula over here, that E is equal to, I'll just write it out in full again, is equal to V plus IR, that our at V is equal to 0, our IR is equal to our EMF. So that's 4.5 is equal to the I times the R. Now this one over here, when we look at that, that is about 3.7 amps. So that is when your V is equal to 0. So we get that. That's 3.7 is equal to 4.5 R. And when I divide that out, I again get R is equal to be about 1.2 ohms. Now, does this make sense here? Is this making sense? Well, what's actually happening here is that our V is 0. Now, when does that happen? That means when I basically make this R equal to 0. So I make this I turn the dial on this variable resistor to make this 0 resistance. So therefore, the V across there is going to be 0, and therefore you're going to have a very large current, the maximum current that you can have of 3.7 amps. And that 3.7 times your resistance in here would equal your V from this formula over here. V is equal to R times I, or I times R. And so we get two different ways of working out this 1.2. Now, I'm going to need to go back here to discuss this, but let's just read the question through, then we'll need to go back to the diagram. The battery in C is used to power a source of electrical device. The device is given by 0.8 volts, 1.5 amps. Complete the circuit to show how the battery may be connected so that the device operates normally. Calculate the value of the other component you may use. So we want the situation over here. We want actually a 1.5 amp current. Now let's just go back here. When I have a 1.5 amp current there, I have that it will deliver a voltage, a potential difference for the circuit of about 2.7 volts. So remember that value, we're going to use it. Going back to my diagram again. So this voltage is going to be 2.7. The potential difference across there is going to be 2.7. I'm going to need to put another device in here so that I get 0.8. So therefore, across here, I'm going to need a potential difference of 2.7 minus 0.8, which is equal to 1.9 volts. So there's going to need that. What will my resistor be? Well, we know that it needs 1.5. So R is equal to V over I. We're going to get 1.9 volts divided by our I, which is 1.5 amps. And when I divide that, 1.9 divided by 1.5, I get 1.27 ohms. There. So I'm going to need a resistor in series with a resistance of 1.27 ohms. That will create a potential difference there of 1.9 volts plus the 0.8, which will match out 2.7 volts, which is across the cell.